When you type a prompt, the model doesn't read your words. It sees math. Your sentence is instantly chopped into subword tokens, mapped to a vocabulary dictionary, and translated into a flat sequence of integer IDs. This split bar chart tracks the allocation of global AI compute. 2/3 of all AI compute is now inference. By 2026, the majority of the world's accelerators spend their cycles serving models rather than training them. The scale of this transition is massive. In May 2026, Google disclosed they were processing 3.2 quadrillion tokens per month across their ecosystem. That is an annualized rate of nearly 38 quadrillion tokens. Training a frontier model is a fixed capital expense. You burn the cash once to produce an asset. Inference, however, is the cost of goods sold. It recurs on every single query forever, scaling linearly as long as users keep asking questions. As inference volume grows exponentially, the price to serve those tokens is collapsing by roughly 200 times per year. Cheaper tokens don't reduce overall spending. They unlock new workloads faster than the price falls. This is the Jevons paradox in action, driving the entire AI economy. To understand how this economy operates, we have to look inside the data center. We are going to take exactly one 12,000 token prompt and follow it through 15 specific physical and logical stops. Following this physical journey reveals exactly how specific latency budgets and memory constraints determine the underlying profitability of the service. Step 1 happens on the CPU, where the tokenizer translates your string of text into integer IDs. Step 2 is the API gateway. In sub-millisecond timeframes, the data center's front door terminates the TLS connection, parses the request, and applies coarse rate limits before any expensive hardware is touched. Before it reaches the GPU, the request hits Step 3, authentication. The system resolves your API key to an organization, checks spend caps, and assigns a billing tier. This is the boundary where a stream of anonymous bytes becomes a metered and isolated unit of work. Next is the load balancer. In traditional web traffic, you might use a round-robin system to distribute requests evenly across servers. In large language model serving, doing that often wastes resources because it ignores the heavy computation required for long prompts. Step 5 is the inference router. This map routes identical prompt prefixes to a specific GPU node. If a prompt was processed recently, that node already holds the data. By routing here, it bypasses expensive computation, converting a massive input into a near-free cache hit. Simultaneously, the router selects the exact hardware and kernel execution plan required for this specific request. The optimal chip and math precision change depending on the exact shape of the workload. Before a single mathematical calculation occurs on an accelerator, the financial outcome is largely decided by these routing decisions. These first 5 steps establish the efficiency of the entire pipeline. Once the request lands on a GPU, it splits into 2 distinct physical regimes of execution: prefill and decode. Prefill processes all your input tuppence in parallel. It is a massive matrix multiply that completely saturates the GPU's tensor cores. Because it relies on raw math, prefill is compute-bound. It determines your time to first token. This roofline chart shows exact hardware limits. Prefill sits high on the compute-bound y-axis, while decode is trapped low on the memory-bound x-axis. Generating tokens requires streaming the weight tensor out of memory. This bottleneck leaves GPUs starved, utilizing only 40% of their capacity. To fix this underutilization, we reach Step 6, the scheduler. Its primary tool is a technique called continuous iteration level batching. Instead of waiting for a static batch of requests to finish, the scheduler admits new requests and evicts completed ones at every single forward pass of the model. It interleaves multiple sequences, so the hardware is always working on something. Closing that utilization gap through iteration-level batching is a core requirement for sustainable GPU unit economics. Inside the attention layers, calculating the relationships between tokens requires complex math that scales quadratically. Recomputing every pass token for every single new step is too computationally expensive. So in Step 7, the system stores the results in the key value, or KV cache. The problem is that user sequences grow to unpredictable lengths. If you allocate memory in contiguous blocks, finished sequences leave awkward gaps behind, stranding up to 80% of the GPU's memory. Engineers solved this with paged attention. The KV cache is split into fixed virtual pages. They don't need to sit next to each other physically, and the instant a sequence finishes, its specific pages are freed up for the next user. This optimization is critical because of Step 8, the physical constraints of GPU memory. The finite space on this package holds model weights, active workspace, and KV cache. Whatever capacity remains dictates the hard ceiling on how many users a provider serves simultaneously. To squeeze out more capacity, we move to Step 9, high bandwidth memory, and Step 10, CUDA kernels. By quantizing the model weights down to lower precisions like 8-bit or 4-bit floating point, the system reads fewer bytes per token. That immediately reclaims critical memory bandwidth. Simultaneously, techniques like kernel fusion collapse multiple mathematical operations into a single step. This traps the intermediate data in the ultra-fast on-chip SRAM, minimizing the slow, expensive round trips to the high-bandwidth memory. In the business of inference, memory is directly tied to revenue. Every bit shaved off a weight and every page saved in the cache directly translates to an additional concurrent user on the balance sheet. Our specimen prompt fits on a single chip, but frontier models operate on a different scale. Trillion parameter configurations simply do not fit on one GPU. They have to be sharded across multiple machines. This requires tensor parallelism, where the matrix math is split across GPUs. After every layer of computation, the partial results must be synchronized across all the chips, multiple times for every single token generated. To handle that synchronization, we hit Step 11, NVLink. This ultra-fast interconnect fuses the GPUs within a single rack into one logical accelerator, demanding up to 1.8 terabytes per second of bandwidth per GPU just to keep the system moving. Step 12 is the switch. Inside the rack, a dedicated crossbar allows dozens of GPUs to transmit data to each other simultaneously, at full speed, without blocking any of the traffic. For packets traveling beyond the rack, Step 13 routes data through the network interface card, or SmartNIC. This dedicated processor offloads network congestion control and encryption directly from the host CPU. Once data leaves the local rack scale-up to main, it enters Step 14, Ethernet scale-out. Modern infrastructure relies on RDMA over converged Ethernet, bypassing CPUs completely to allow remote GPUs to read memory directly over these fiber links. But pushing this much data over fiber has a hidden cost. The optical transceivers required for these connections burn massive amounts of power, pushing the industry toward co-packaged optics just to keep the energy demands manageable. For frontier AI, the network is not an external communication channel. It sits directly inside the math loop. When you synthesize all 15 steps, they point to a new overarching architecture: disaggregated serving. Look at this architectural flow. One pool of GPUs is dedicated solely to the compute-bound prefill phase, and streams the completed KV cache over the network to a separate pool of GPUs specialized for decode. By physically separating the compute-heavy hardware from the memory-heavy hardware, data centers can scale and tune each phase independently. It is the most effective way to maximize hardware utilization across the entire facility. For builders and investors, the lesson here is strict. A business model built purely on raw software speed is fragile. Compilers and open-source tooling are rapidly commoditizing those kernel-level optimizations. Durable enterprise value actually accrues at the physical bottlenecks. It relies on proprietary scale-up interconnects, pure memory bandwidth, and the sheer availability of power and cooling infrastructure. As data center capital expenditures reach $750 billion, profitability is tethered to physical efficiency. The terminal metric for the entire economy is tokens generated per watt.